Okay, welcome back to this last session of our workshop. I'll be your host for this session, and good morning to our friends from Northern, Central and South America. So we have a few more speakers, plus we'll have a final discussion, so we can discuss together about what kind of the outcomes of this workshop. So our first speaker for this session is Wolfram Schmidt, who unfortunately is not here. Unfortunately for us, fortunately for him, because he's on holidays somewhere in the Northern Sea. And Wolfram is a researcher at the Federal Institute for Materials Research in Berlin, Germany. Perhaps most of you are familiar with him. He is into a series of educational and scientific networking programs, and we have mentioned some of them during this workshop already. Okay, so I'm just going to share the pre-recorded video.
Welcome everybody to this talk about multidisciplinary approaches toward an inclusive circular urban built environment. My name is Wolfram Schmidt. I work at BAM in Berlin, Germany, and I would like to thank the organizers for having me at this conference, and I would also like to apologize that I cannot be here with you live, but there was a clash of duties, and unfortunately I cannot be here, but I would like to encourage you to get in contact with me afterwards if you have discussion items or questions. But now, without further ado, I would like to come to the human and societal crisis that we face in the next century, which is war, hunger, health, migration. But beyond these societal challenges, we have more technical or environmental challenges like habitat, infrastructure, urbanization, environment, and sustainability. And if we take a closer look at that, we can see that the construction industry has a very heavy contribution to these challenges. The construction industry is growing, so this contribution will be bigger and bigger. And already today, according to the United Nations Environment Programme, the carbon emissions and also the energy demand of the built environment make out about 40% of the global values. And the construction industry itself contributes already with about 10% to that. But when there is such a huge global demand, we can certainly consider it as a challenge, but we can also consider it as a potential, because if we just make it more sustainably, we can create great leverage towards a betterment. The construction industry can really become a game changer if only we can create sustainable construction where the environment is protected, where more climate-friendly materials are being used, and where this also creates markets. Because when people can use sustainable construction to create livelihoods, automatically those human and societal crises I mentioned at the beginning, like war, hunger, health, and migration, become better. And therefore urbanization and construction in general can contribute also to those more societal and human challenges we face. That means if we build something, a construction that automatically interacts with the environment and vice versa, that is well known, but we also have to consider that construction also interacts with how societies behave, and that is also a mutual effect. And urbanization, cities are the places where all this comes together: environment, societies, construction, and therefore urbanization processes can really become critical for the future of humanity. We have to make sure that our future cities are not only structurally safe. We also have to make sure they are environmentally friendly, but particularly we have to also consider that they are socio-economically sustainable, that cities are built for the people who live in these cities, which is not the case today, and where we have to change our mindset. Because if we just fail one of these items, we fail to have a sustainable urban structure. And much of how potentials and challenges can unfold in the urban development depends on whether the city is already existing at a high population density, or whether it is a low density region which can still develop over the course of the next decades. And I'm not getting into the details of that figure. You can read it if you like in this publication, but it seems that a high density situation and a low density situation seems to be very crucial for how cities evolve in the future and how people perceive their cities. And I would like to give you that example of a workshop I did with children in a very neglected settlement in Nairobi, in a very urban environment, Mukuru. And I asked the children how they dream the city of the future, and they said they want to have more space, more green, more animals, which is really a rural environment. And then I did the same exercise with girls and young mothers in a place which is very rural in Bagamoyo in Tanzania. And here the answers were short distances to services and health facilities, good access to educational institutions, which is rather the dream of an urban environment. So that is a very clear indicator that we really have to take care that we do not over-urbanize those already urbanized regions that exist, but rather invest into the medium and the smaller cities, which also help developing the rural environment. So cities really have to grow to the benefit of the people who live in those cities. And you've seen that my examples were all coming from Africa for a good reason. The urban population all over the world is growing, but in sub-Saharan Africa, the urban population is growing dramatically strong, much more than in the rest of the world, and therefore Africa has a very specific role if we think about urbanization processes. 13 out of the 20 most populated cities in the future will be on the African continent, of dimensions which we have never seen before, like Lagos, 88 million inhabitants. That's incredible. And what is so interesting about that is that of those cities that will have been built in the year 2050, only 20% have been built already today, which means over the course of only the next 30 years, 80% of these cities will have to be built in the most sustainable way that we can imagine. So we have to really stop discussing this. If this is done, then this will happen, and waste our time. We have to bring those players who really want to have this sustainable change, we have to bring them together and act now. And even if we only find the second best solution, it's still better if we find it today than to wait for another 30 years to continue to repeat the mistakes of the past and then start with the very best solution. So we really have to act now, because we only have 30 years time. And we have to see the potentials of Africa. If we take this as a threshold, 2.7 kilotons of carbon emissions per capita, to keep the global warming below 2 degrees Celsius, we have to see that most of the regions in the world are way above that. They do not qualify as a role model, but sub-Saharan Africa is below that threshold. Sub-Saharan Africa can approach this threshold from below and does not really have to give up on privileges and can develop something more sustainably. And this way, sub-Saharan Africa can become a role model to the rest of the world for green, sustainable urban developments. But that certainly starts with the materials. So there are a lot of structural materials that can be used, earthen materials, timber, steel, concrete, for example. What is the best? So timber is often considered as the healing, and timber is very beautiful, and if a sustainable timber supply is chosen, it can really be a carbon sink, but unfortunately in most parts of the world the timber supply is not from sustainable sources, and in many parts of Africa, deforestation has really caused dramatic environmental challenges. So it has to be taken very carefully. Steel is known to have a very high carbon footprint, but there are tensile loads, and steel is the best material for that, so we cannot entirely avoid it. And then if we take a look at recycled steel, for example, the carbon footprint becomes much better. Earth materials are remarkably low in their carbon footprint, as long as we do not use cement, but unfortunately earth materials require maintenance, and therefore people use cement as an addition to the earth materials, and then all of a sudden the amount of cement becomes very high for a very low strength. And then we completely underuse this high carbon impact material, cement, and then it stops to be very sustainable. So also this has to be considered a critical aspect. Then if we take a look at concrete, it is much better than its reputation. And here in the figure on the top, you can see that the carbon footprint as well as the embodied energy is much lower than most other materials, including timber and so on. So concrete is not that bad. Cement is a little bit worse, but it's only the glue and we can reduce it. The positive thing about the concrete is it can be produced everywhere. It's a local business, it's easy to handle, and it's reasonably cheap in most parts of the world. But in Africa particularly, it's extremely expensive. Here I made this calculation. In 2009 it was most dramatically when I found out that an average income earner in Germany has to work for half a day to purchase a ton of cement. But in the Democratic Republic of Congo, an average income earner had to work for 323 days to purchase the same ton of cement. And that is really a huge number. So also concrete is a price question, and where the supply chains are not very good. So with respect to the materials to be used, there is no single answer, and definitively there won't be a marvel solution. We have to live with what we have, but we have to consider good engineering. That requires that we use materials according to the load case. When there is tension, we need steel. If there is flexure, sorry, we can use timber or we can use reinforced concrete, and for compressive loads, normal forces, we use concrete or earth materials depending on the load. We have to build more hybrid. And we also have to keep it low-key. So building a kilometer in the desert high doesn't make a lot of sense, because if we stack story upon story, the lower stories always have to carry the sum of the stories upon them. And that requires very huge cross-sections for the vertical elements. Or in other words, if I want to stack 50 stories upon each other, I require 25.5 times more materials than if I would take these stories and just disperse them horizontally. So we don't have to discuss about saving 5 or 10% of cement if we waste our concrete here. So low-key, also keeping the span width low, sometimes a single column can save us a lot of material. And eventually it is important, like for food, to use local materials to become sustainable. So if we take a look at that load case, low-key, local, we all start with an L. So let's call that the 3L principle for good engineering and good urban construction. And I would like to give you an example how that can work, and I would like to give that example based on concrete, because we can discuss about materials, but concrete is the only material that is sufficiently available on Earth to build our structures, infrastructures, underground structures, and so on. So concrete is there for urban construction. It's also a good material because we have a lot of vertical loads. Concrete is good in that, and if we keep the construction heights low-key, it's really a good choice. How can we make it more sustainable from the materials perspective? We have to reduce cement and replace it by supplementary cementitious materials which are more sustainable, and we have to make full use of cement as a binder by reducing the water-cement ratio and probably using chemical admixtures to support that. And here in Africa we find local materials. So cement replacements can be based also from agricultural wastes, because agriculture is a future business in Africa. like maize cobs or rice husk or sugarcane bagasse or cassava peels. And also for the chemicals, we can use bio-based chemicals, which can help replacing petrol-based chemicals like gums or starch and so on. And an example I would like to highlight here is the example of cassava, which is a food that feeds like 500 million inhabitants in the world. And in Africa it's particularly important, and it has been growing in production over the course of the last 60 years, and it will continue to grow because it also grows on marginal soils. So today cassava is being harvested. After that it's peeled, and the peels still contain a lot of starch adhered to them, and afterwards the inner part of the tuber is converted into a food product, quite delicious. For example, if you travel to West Africa, you should try a fufu, which is made of cassava. But then the rest of this plant is not digestible for animals. So what happens is that people dump it away and consider it as a waste. But if you consider it as a resource, it qualifies to produce a water reducer for concrete. It qualifies to be energy producer, and after burning it, the ashes qualify as a cement replacement. And that's really remarkable, because before there was no value in it, and now you can create a value chain in the chemical industry as well as in the construction materials industry without competing. And that is the most remarkable thing in it. And cassava is only just an example, but there are much more possibilities to use agricultural wastes and convert them into construction materials. And here you can see for different countries how much of the country's cement production can be replaced by bio-based resources. At the moment that doesn't seem to be too much, like maybe 5%, 4%, 3% for some countries, but we have to consider that at the moment the efficiency of agriculture in Africa is much lower than in the rest of the world. So there's a tremendous growth potential, and 60% of the global arable land areas which are not yet used are on the African continent, which is another huge growth potential. And all of a sudden we talk about 15, 20, 25% of replacement possibilities, and then we are even higher than the ratios that can be replaced by fly ash or by ground granulated blast furnace slag, for example, which are established in the industrialized countries. So the farmers in the future can not only deliver farm products to the cities, but also use their wastes to convert them to materials, chemicals, and energy. And that creates new employment perspectives in urban development. And with the urban growth and the urban construction, value also flows back into the villages, where it can contribute to the rural development. And just to show you quickly how that works, if we take the agricultural wastes, the residues will get into a wet process where we can obtain chemical admixtures. The residues of that process get into a pyrolysis where we can obtain chemical precursors, which can go into asphalt industry, for example, or sealants. And the energy that is produced from here, carbon-free to the moment, can be used to fire a brick process. And the residues, the biochar from the pyrolysis, can be added to the brick production as an internal fuel. And then from the kiln you do not only obtain the bricks, but you also obtain a pozzolanic ash. And with the chemical admixtures that help reducing the water content, and with the pozzolanic ash that helps reducing the Portland cement clinker content in concrete, we can really create green urban construction materials. Certainly the decision trees here and the process chains are very complicated. I'm not getting into the details of that figure, but I would like to highlight that in between there are always decisions, and these decisions have to be made by human beings. And that is the important part of it. The decision makers in these urban processes and the decision process to create construction materials and value chains and supply chains, they have to work hand in hand. They cannot work as a standalone person who's just an engineer or just an investor or just an architect. We have to work together, and we have to communicate with the different disciplines, and we have to see the different perspectives as well, and bring them together. And this human factor is so important. We always believe that technology will save us, We dream about a brave new world where robots take over construction techniques, where robots even take over thinking, and the calculation and the human aspect in this process becomes marginal. But the reality is, it's not like that. I've been to the highest mosque tower in the world, which is in Casablanca, in Morocco, and I was completely overwhelmed when I've seen the architecture and the crafts work there. There were a lot of patterns, like you can see on the right side, which would be perfect for a 3D printer, because a 3D printer could make this very efficient and perfect. But the reality is I was overwhelmed because it was beautifully imperfect. It was made by human beings, and that gave it a heart and it gave it a soul. And that was the overwhelming moment, which is probably more sustainably at the end of the day than all the efficiency of a robot. And then this, in combination with the standard, becomes a little bit dangerous, technology and standards, because standards are a little bit like medicine. I'm not at all against them, but you have to use them in the right dosage, because if we overdose, like in medicine, they become poisonous. And the problem is you always look at the price, so there's no driving force to outperform the standard, and therefore a standard becomes nothing but the certificate of officially approved mediocrity. And mediocrity is the last thing that we require to become more sustainable. So technology is good, standardization is also good, but we have to have a human being in between to balance these things, to make sure that technology and standardization serve to the society, to the humanity, and to the sustainability. And I would like to give you a very drastic example how this can fail. This is a picture of Cape Coast Castle in Ghana. If you should travel there, please visit that. It's very important. It's a beautiful, nearly romantic building in a very colorful environment, very beautiful. But you have to know that this was one of the slave traders' hubs in West Africa. And right in front of the entrance of the church on that campus, hell broke free, because underground human beings were stacked in their own feces, hundreds of them, waiting until the next ship docks. And the human beings will be forced to leave the door of no return to enter the ship, where they either have a destiny where they die in the ocean, or where they become slaves for the next and the second next and the second next generation. And the consequences of this structure, which was built very efficiently, optimized for efficiency, it was built according to the state-of-the-art technology at the time, according to the standards that apply. But still, the implications of building that structure still last until today. So we always have to see the full picture. We have to consider that the consequences of our actions can outlast our own lives by far. And with that mindset, we can start to think about becoming more sustainably. And the Falconers Consortium, it's a consortium, female academic leadership network for conscious engineering and science towards sustainable urbanization. I'm happy to be part of it, even though I'm not female, but I think that's a very tremendous network that wants to look at urban processes from many, many different disciplines, and from a Falcon's perspective, from the top, so where we can see the holistic picture, but at the same time, we want to have a sharp eye on the details. I think that's very important for sustainable urban construction. So what is important is that we have to stop being appliers of technology. We have to become conscious engineers. If we work all together, hand in hand, then we have the power to change the urban environment to the better. But that requires a different way of education, also of the next generations, who really have to stop being technicians only, but they have to become conscious. That means they have to be also taught the beauty of nature, history, markets, social behavior of human beings, the microscale as well as the macroscale. Only then we can learn together and grow together. Therefore, it's important that the decisions for the future should not only be made by today's decision makers. Today's decision makers, they have to mentor the next generations to become more sustainable future decision makers. And at the same time, this does not apply only for the students and school children, but also for the youngest. And we also have to listen very carefully to the youngest, to learn from them, to make our decisions already now for the future of the next generations. And if we take that into account, then we have a bright future and we can build urban structures, urban environments much more sustainably. And with that, I would like to thank you very much for your kind attention.
Okay, so it was a, sorry, I'll have to activate my video. Okay, it was a brilliant talk from Wolfram. I think it very nicely illustrated the importance of driving the construction industry towards a more local approach, given that transport, import of goods enormously contribute to both CO2 emission and final price of the final product. Okay, so feel free to contact Wolfram if you have any question. I'm sure he will be more than happy to answer to any query. So the exploitation of the local resources will be further addressed during next talk, which will be Okay, sorry, I'm going to mute you, Kola. Okay, next talk will be delivered by Dr. Mark Bediako. Mark is a researcher at the Building and Road Research Institute of Ghana. He is also the head of the Advanced Material Science Division and Civil and Materials Engineering Laboratory. His research is involved in different aspects of concrete sustainability. So please, Mark. You're muted.
Okay.
Okay.
So I don't know whether you can see me in the video.
Yeah, we do indeed.
Oh, okay. So good afternoon from Ghana, and I don't know where people are. So wherever you are from Ghana is good afternoon. So I am presenting today on the topic entitled Some Engineering, Transport Mechanism, and Embodied Carbon of Ghanaian Low-Grade Calcite Clay Concrete. So, okay. Well, so by way of introduction, supplementary materials such as fly ash, slag, silica fume, metakaolin, calcine clays, and some agro-waste materials are attracting some form of attraction within the research community because it has economic value, ecological advantages, and technical benefits. And the reason for its economic value is because literature have found that it reduces the clinker factor. Ecologically too, it also reduces the carbon footprint, of which we've heard from other presenters. And technically, it's known to enhance the strength and transport properties of concrete. So the problem for this study, I have categorized it into two. I'm looking at it from the global perspective, that is the general problem. And then I look at it from the Ghanaian perspective, which is a local problem. So with the global problem, we've heard, yeah. So let me re-emphasize that our population growth and urbanization is an issue in the world. The United Nations has stated that population by 2050 will reach about 10 billion. Currently, we are about 7 billion. and 66% of the people within the world will be urbanized. Africa and Asia is being highlighted as one of the places that will have a higher share of the population density. Aside that too, I mean, many of the African and Asian countries will see higher economic growth. But the point is that all these things will be associated with the overconsumption of materials. And this is a graph that I picked from a document from the United Nations. They are saying that by 2060, if we use the 2011 levels, we're going to increase material consumption to about 400 gigatons. So it's going to increase by 283% as a result of economic growth. I mean, people will be building infrastructure and roadworks, concrete roads, and many things. So the concrete industry is going to play a major role because people, many countries are going to develop. We're going to see higher consumption of non-metallic materials like sand and coarse aggregates. And the point is that when there is a higher consumption of materials, of course, we have to put it at the back of our mind that there's also a higher embodied carbon and energy release. The issue too is that, I mean, people have mentioned it, concrete consumption is responsible for about 9% of the total greenhouse gas emissions. And interestingly, cement generates about 96% of this 9%. So it's very important to look at the cement that we use and see how best we can actually look at reducing its carbon footprint. So let me come to the local problem in Ghana. So Ghana, I mean, is having a booming economy of late, and within African settings, I think that we are doing not bad. We are having a lot of construction activities. Recently, our vice president made us to become aware that we're going to do a lot of concrete roads instead of the asphalt roads, railways we are building. All this construction is using the cement. The point is that we are using almost $400 million to import clinker and gypsum to the country. We don't produce clinker because we don't have very quality limestone in the country. So look at this. I gathered this information from 2000 to 2021 now, as of now. It's very interesting. This is the trend of cement prices over the years. And I can tell you that from 2000 to 2001, the price of cement per 50 kilogram in Ghana has increased by 1,678%. That is very, very huge. So as a Ghanaian, as a researcher, this high cost of cement is a local problem, and it calls for an urgent attention for we, the people in the research community. It increased at a rate of 6%. Now, from hindsight, we can see that cement consumption is predicted to reach about 10 million tons. Now we are consuming about 7 million tons. So by 2025, we're going to increase. So, I mean, there's an urgent need for us to do something about this. So that is the local problem in Ghana. So what is motivating me to go into this study? Of course, we have a UN common goal that all member states should look at the rising greenhouse gas within the globe. And I'm also motivated to look at sustainable concrete through the use of clay pozzolan in Ghana. Prof. Otieno made something that was interesting to me, that we need to validate research work. I mean, people have done research on clay pozzolan, but using local material in Ghana, we should validate it. I like that statement. So I've already shown this graph, I mean, part of it, but I'm showing the extension here. Of course, economic growth is going to lead material consumption by about 283%. But then they are saying that through structural change and technology, we can reduce it. to about 167%. So from a little below 400 gigatons to a little below 200 gigatons is very significant. And it's all because of structural change and technological change. I mean, using chemical admixtures and using alternative materials like clay, pozzolana, and earth, we can actually reduce the consumption of materials in the globe. Well, so the objective of this study is to look at processed Ghanaian low-grade calcined clay as a cement substitute for concrete. And then to achieve these things, I have to look at the mechanical properties, which include the compressive and the flexural, and then the transport properties, looking at the suction and the rapid chloride permeability test, and the embodied carbon of the concrete, of the various formulated mists. So these are the materials that were used, the Portland cement in a grade of 42.5.
Okay, I think we kind of lost you, Mark. Do you hear me, Mark? Okay, let's wait for a moment. Let's see if we manage to resume Mark's presentation. And in the meanwhile, let's see if we have next presenter. Okay, I think it definitely lost him. Perhaps let's wait for a couple of minutes. If he will be back, it's right. It will be much worth. I think it's a very interesting work showing how to implement a local approach into the exploitation of calcined clay. This will be explored further also in the next presentation by Fernando Martirena, and following one by Professor Carl Riding. They will talk us about experiences with calcined clays in Cuba and the US. Okay, let's see if Mark is back. Perhaps I will just send him a text message. Okay, so you're back, so let's try again.
Okay. So sorry for that. Okay. Well, please, can you see the screen?
Yes, we do see the screen, Mark. So please go ahead.
Okay, so I can go ahead. Well, so these are the methods that I have already explained it. Okay, so the results for the compressive strength is shown here. The graph is between the compressive strength and the various misses between 0 to 50%. So the key things that were indicated from the graph are these: 10% gave the maximum strength, yes, at all the ages, like this is the 10%. Then the strength increase with increasing period of curing from 3 days to 90 days. And of course, I mean, increasing pozzolana content also decreased the strength. But that wasn't the main point. The main point was that here, the concrete class that was designed was C30. So here, the graph is showing the strength change against the misses. So the C30 has been normalized, but these are the key things. So at early ages, the 10 and early age of 7 days, 10 and 20% was higher than the characteristic strength, which was C30. And then between 10 and 50, concrete produced a higher strength than the characteristic strength of C30 at 28, 56, and 90 days. So these are the strength performance between 10 and 50. Well, so these were the sufficient values. The point of interest here is that the clay pozzolan reduced the sufficient value. It was lower between 10 and 26%. The RCVT results was also very interesting. These are the key things. Within the high range, if you want to understand it, we can pick the ASTM C1202 to actually look at what the values means. So no range, no concrete was within the high range. But the key thing is that a longer period of curing showed that higher volumes of the pozzolans within the concrete resisted the ingress of chloride. So at 40 and 50, it was within the very, very low range at late age of curing. So the embodied carbon, the plot is between the concrete various mixes and then the embodied carbon release from the mixes. So these are the key findings. So the first one was that the concrete without the pozzolan had the highest emission. So this is the line showing a highest emission. And then the emission reduced as the pozzolan content was increasing. So that was the trend. And there was also a marginal increase within the other constituents. So if you look at coarse aggregate, fine aggregate, and the chemical admixtures, you see that there was a marginal increase as compared to the OPC. Here too, you can see that one. Yeah, so and so on. So in conclusion, what we're saying is that half of the cement and half of the pozzolan was able to achieve the characteristic strengths. So the values were 32, 34, and 30 MPa at 26 and 56 and 90 days. So that was it. The sufficient values was also very positive. When we used the pozzolans, it was reduced by 10 to 26%. The embodied carbon, which is very important to UN and the world, showed that increasing the pozzolan content to about 50% can help you achieve a lower embodied carbon, which was about 222 as compared to the control, which is about 399 kilogram carbon equivalent. And then beyond 28 days, that is the 56 days, we have concrete containing pozzolans resisting the ingress of chloride. So it means that we can use about 50% pozzolans to actually produce reinforced concrete, which is very, very good. And the last one, 40 and 50% pozzolan concrete mixes, fell in the range of a very low chloride permeability characterization. And that is between 100 and 1,000 columns at 90 days. This shows that 50% pozzolan is suitable to stop chloride attack in concrete than 100% cement concrete. So in Ghana, we say Medasepa, which means that thank you very much. So I bring my presentation to an end. Over to you, Luca.
Okay, thank you. Thank you, Mark, for this nice presentation, for illustrating the Ghanaian scenario. If you have any question for Mark, please use the Q&A feature of the platform. So let's welcome our next speaker, Professor Fernando Martirena. Fernando is the director of the Center for Research and Development of Structures and Materials at the University of Central University de las Villas in Cuba. And in latest year, he's been dedicated to the introduction on the market of the LC3 cement. Is a very promising new cement. Actually, we can call it reality, I think, nowadays. So please, Fernando, you can share your screen.
Yes. Do you see my screen now?
We do, yes.
Okay. Thank you very much, Luca, for the introduction. Also, I want to thank the organizers of this seminar for inviting me here to share our experiences in introducing a novel cement, especially in the context of climate change mitigation. Myself, I'm a professor and director of a research center at the Central University of Las Villas in Cuba, but also work with the Swiss-based company Eco Solutions in Switzerland, providing advisory service to the cement industry. I'm also happen to share the RILEM technical committee on calcined clays and supplementary cementitious materials. I have more than 12 years of collaboration with Professor Karen Scrivener in Lausanne in studying the calcined clays as supplementary cementitious materials. In the last few years, this group has been integrated also with several Indian partners, the Indian Institute of Technology in Delhi and Madras, and we have a global team now that is endeavor in introducing this cement. Coming to our subject, I mean, all of the presenters before me discussed already the impact, so I will not talk much here. The impact of the cement industries, you know, after the power generation industry, the cement industry is one of the largest CO2 emitters, more than 8% of the world global CO2 emissions. And not because cement is it's a nasty or not environmentally friendly material, but because it is used at a very high, massive scale. Last year, production was more than 4.2 billion tons. I mean, no other material is produced at such a scale. And therefore, even if you have low emissions because of the massive amount of manufacture, you have a big impact on the cement is used for building up the infrastructure of countries under developing countries. We have seen that decline in production in China. We're going to see it further, but countries like India that have almost the same population as China and 6 times less per capita cement consumption are going to definitely increase cement consumption in the forthcoming years. And Africa, of course, is not an exception. I mean, many African countries need to build ports, buildings, roads, infrastructure. So there's going to be a rise in cement production with a contribution also in increase of CO2 emissions. So we have to find ways of making cement production more sustainable. And there are several ways, and it's already discussed everywhere in the forums. You can use alternative fuels, you can increase the efficiency of the kilns, but the most practical way, and everybody agrees with this, is to reduce the clinker factor, because clinker is the most energy intensive component in the cement, and there are materials, some of them byproducts like fly ash and slag, that can replace clinker successfully in the cement, but also and produce the cement with less clinker, therefore less CO2 emissions and similar properties. We also have limestone, natural pozzolans. But what we're seeing in the last few years is that there's a plateau in the clinker substitution rate. On one side, because if you increase the clinker substitution with these normally used pozzolans, you compromise strength, especially early age strength, and that's bad for concrete. But the most important thing is that the availability of many of these supplementary cementitious material is not in the same order of magnitude as Portland cement production in a year, as you can see here. For instance, slag and fly ash, which are the most common use supplementary cementitious materials, you see their availability would be something like, I mean, the highest would be 15%. And even in the case of fly ash, we're using only a small part of the fly ash produced in the world in coal power plants. Therefore, the only materials that are widely available and that could be suitable supplementary cementitious materials are limestone and calcined clay. In the case of Africa, because of the geology, I mean, the geological history of Africa, there's a scarcity on limestone. Therefore, you barely see clinker factories in Africa, except in a few countries where you have some research of limestone. And Africa is mainly a continent importing clinker from elsewhere, especially from Europe. And that makes cement very, very expensive because you have to pay for transportation, and also you have the external dependency on the market. However, if you look at the geology of Africa, you realize that it's full of clay everywhere. You go to every country, subsoil, topsoil, and you find clays, especially the good one, which is kaolinite clay, which is the one in yellow here. So it's a very, very interesting alternative for countries, and for African countries, there's a very good opportunity. I was pleased to see presentation before me about calcine clay in Ghana, but there you will see here that there are many other countries that are using this so far. So the challenges for most African countries are, first of all, to reduce clinker content in cement due to the high cost of imports, but also due to environmental reasons, if you want to really reduce carbon emission. And to do so, you have to find locally available supplementary cementitious materials. In this regard, I want to make the case that calcine clay would be a very interesting material for Africa, which would have also the impact of reducing transportation, because you can set the plant near to the source of the supplementary cementitious material. And this is where the limestone calcine clay cement plays a role. This is the material we've been developing in the last 10 years together with this international team. You see here on the left side of your screen, you see that we have pure Portland cement, you have Portland pozzolan cement, and then you have LC3. The interesting thing of LC3 is that you have only 50% of clinker, you have a higher amount of limestone, 15% limestone, and the same amount of pozzolan used in pozzolan in cement, so 30% pozzolan, and you are able to achieve the same strength as a pure Portland cement at all ages. And that's the most important thing. You're increasing clinker substitution further, but you're retaining the strength of the material. But also through the substitution of clinker, you replace 15% more clinker than even Portland pozzolan cement. You're able to make a higher contribution in terms of carbon reduction. But also clinker is the most expensive material in cement production. And since you're reducing this, you also have a contribution to cost. And to our surprise, in the applications we have seen, and it was discussed here before, that concrete made with calcine clays, they have excellent durability. Here's the science behind that. I will not give too much details, not to bore the audience, because everything is already published on the public domain. But we have three reactions taking place at the same time. First, the pozzolanic reaction, which is normal, well-known between clinker phases and calcine clay. Also, we see a dilution effect of clinker by the filler effect caused by the limestone. It's also well-known, well-described elsewhere. And the new thing here is that we have a synergy between calcine clay, the alumina available in calcine clay, and the carbonates available in the limestone to produce new reaction products that contribute to have a denser microstructure, thus reflecting in a higher strength and a higher durability of the system. That's the basis behind all of this development. I mean, if you compare concrete, for instance, that like was presented before, only with calcine clay, and you can even extend further the clinker substitution by adding limestone, and that will not compromise the strength of the system. So in terms of production, Africa needs to face the industrial production in calcination units, existing cement plants, new grinders, etc. But also we have explored, and for the sake of time, I will not discuss this in this presentation, but we have also implemented in Cuba and in other countries a local production using as a source of calcine clay these crushed fire clay bricks. And that's very, very interesting for, especially for popular development projects in villages and everywhere. So here is the scheme of this LC3 production. So basically you take suitable clay, you fire it at 800 degrees Celsius, then you can either blend it with clinker and gypsum and limestone and make the cement itself, or you can produce a mineral addition, we call it LC2, by grinding it, blending it with limestone and grinding it. Those are very interesting choices for production. Of course, you need to have this clay, suitable clay. You need to process this clay where you have to go to the brick industry to get expertise. And then you calcine the clay and then you do the whole thing of blending until you use it in concrete. We have accumulated some industrial experience producing what we call the LC2, because here we have a mineral addition that has calcined clay, limestone, and gypsum, so it's properly sulfated. And you can use it very flexibly by blending this with a cement that is available in the market. And at the level of the mixer, you have a composition of the binder similar to the composition of the LC3. And to our surprise, when we compare here, for instance, we see that first graph is the Portland cement along the strength. And here is when you take half of this Portland cement, 50%, and 50% of the mineral addition, you see that you're even outperforming Portland cement by adding this. So you're having a material that you're replacing half of Portland cement and you're not compromising the strength, but increasing the strength. And also you realize here that if you try to increase the amount of Portland cement, I mean, you have some minor contribution to the strength. So it's not a big deal. In terms of cost, I encourage you to download, this is for free, this report made by the company Cementis on the feasibility or financial attractiveness of LC3, where they have studied different scenarios. I mean, different distance from the clay quarry, different production scenarios, and in every scenario, the cost of LC3 is at least 10% lower than the cost of traditional cement produced over there. And the good news, especially for African countries which follow, same as Cuba, they follow the EN standards, is that the TC51 on cement, they have recently released a new standard, still to be ratified individually in each of the UE countries. But these standards, and you see it here, it enables to produce a SEM2, a Portland composite cement, with 50% clinker and a combination up to 50% of other materials, including calcined clay and limestone. So LC3 is already present in its original composition in the European standards, and that's a very good news. In terms of CO2, again, remember 60% of the carbon emissions associated with cement productions are associated with the decarbonation of limestone, which is 80% clinker raw materials. So if you replace clinker by any material, you're automatically reducing carbon emissions. Of course, here we are calcining the material, so we have some collateral CO2 emissions associated with the fuel. But when you check this and you make this analysis, for instance, here I'm taking the Global Cement and Concrete Association benchmark figures, where it's a fully optimized cement, and you compare here the CO2 saved. For instance, compared to the same one, we're able to reduce 40% of the carbon emissions compared to a SEM2, and we can reduce between 18 and 25%. But we have to bear in mind that we have to compare to the same one, because we're achieving the same strength results as the same one, meaning that this is a huge contribution in terms of impact on CO2. And that also brings some opportunities for African countries. You see, the cost of a ton of CO2 in the global market, especially in Europe, right now it's around 50 euros. It's a slightly higher the cost of 1 ton of cement, so the average cost of 1 ton of cement, and it could even go higher in the forthcoming years. So incentives associated with this could be a very good driver for introducing these kind of cements in Africa, and you consider, bear this in mind. But also there are very interesting opportunities for cement producers, which is to produce very low clinker cements. Remember, concrete is only 40% of cement applications. The rest is masonry, finishing works, other works, and we can produce a cement that has only 35% of clinker. And check this, this is the green bar here. And this concrete, even this cement, even from 7 days on, has almost the same strength as the other and any other cement, traditional cement produced. So that's a very interesting opportunity. You guys in Africa already have this in place. I'm presenting here, taking this information from the presentation of the company Simpor in January this year in Ivory Coast, where they have already a plant in full operation, producing 2,500 tons of cement per day. There's a new one by the same company planned to be open in Cameroon, and there are some investors now exploring the market in Ghana. So I can anticipate that Africa is going to be the core of this LC3 technology in the forthcoming years, and that's very good news for you. From our team, we offer the assistance, technical assistance, our expertise. We have a technology resource center in India. We have another one here in Cuba. We're working with the west part of Africa. India is working with the east part of Africa. So we are available. We have developed a full protocol to assist companies in the introduction of LC3 with standardized testing and everything. So we can really make this happen and happen very quickly. For instance, we were there in Ivory Coast assisting the local company introducing this. And I think that if Africa really wants to embrace this technology, you really have to create capacity of that. We have a pilot plant in Cuba where we do trial operations. It's fully sensor monitor, and it's, I mean, we offer you all of these facilities in order to introduce the technology in Africa. With this, I'm coming to the end of my presentation. As concluding remarks, you know, Africa has to lower the clinker content of cement. You have the good material, good place everywhere. LC3 cement is a good choice because you're having a strong cement which you can use in concrete, but only 50% clinker. There's already ongoing projects and a full plan in operation in Africa, and at least 2 more plants will be started in the next 18 months. And but also you need to create LC3 Technology Resource Center in order to accompany the dissemination of the technology. Thank you again for your interest. Thank you, Luca. And it was really a pleasure to share with you my experience. Thank you.
Thank you very much, Fernando. I was actually going to ask you about Ivory Coast, because I remember this being told during one of the last offline conferences before COVID. So it's good that you updated us about this. There are a couple of questions from the audience. So if you can shortly elaborate on this. The first one is what are the differences in terms of engineering properties between LC3 and calcined clay cements, I guess, without limestone?
Well, actually, the problem with calcined clay cements, where you're using, let's say, 70% of Portland cement, 30% of limestone, of calcined clay, is first of all, you don't use the synergy between the limestone and calcined clay, and you cannot reduce it. I mean, it's very likely that if you lower the clinker content down to 50, you get a much lower strength than if you do it by a combination of 30% calcined clay, 15% limestone. I mean, a 2-to-1 molar ratio. That's the first thing. I mean, contribution to strength, but also water demand. Calcined clays, they are known to have a very high specific surface, and they increase the water demand to a great level. So if you introduce limestone, you're introducing a material that has less water demand, and you're kind of mitigating the high water demand produced by the presence of calcined clay. And also, and ultimately, it's a matter of cost also. I mean, for the clays, calcine clays, you need to spend energy, so there's a cost associated to that, whereas limestone, it's only the extraction cost, what you have there.
Okay, and the second part of the question, I think is very interesting, was, is there any specific requisite for the limestone to be used in LC3? Can it be also dolomitic limestone or some other source of carbon?
Very interesting question. Remember, in our system, we only need the carbonate ions. So we can use both calcite limestone and dolomite limestone. I mean, it doesn't matter. And this is a very good news, because normally when you have a clinker production facility, you dump the dolomite, because if you use dolomite and you calcine it to produce clinker, you can collaterally produce perclase, which is very bad for durability. Whereas here, I mean, you don't have any impact on durability. You can use magnesium limestone and absolutely no problem. And sometimes this is a waste of material. And in terms of the quality of the limestone, we can work with a very, very low quality. I mean, the lowest quality in the market would do a job, because the degree of reaction of limestone in the system is around 10%. So you only need that small part of the limestone reacts.
Okay, thank you very much, Fernando. Thanks again. So we can move to the next speaker, who is Professor Kyle Riding. Professor Riding is a lecturer in civil engineering at the University of Florida. His research is focused on different aspects of novel cementitious material. He's an active member of both the American Concrete Institute and RILEM. We have pre-recorded the talk for him, so please let me just share the video. Okay, here it is. No, sorry, was just the audio. Okay. This one, let me share my video. Okay.
For inviting me to speak to you today. I'd like to use an example of calcine clay that has the potential for use as a supplementary cementitious material in concrete as a case study in how we can look to the past for solutions to our future problems and current problems. So as part of that, one of the issues that we have in terms of sustainable development is that Portland cement, which is one of the major ingredients to make concrete, and concrete's the most used building material in the world. Portland cement produces about 5 to 8% of the greenhouse gas emissions from its actual manufacture. So it's a very high footprint, but it's mainly just because we use so much of it. But if we want to be able to reduce the impact of Portland cement production on the world, then we can look at some of alternatives. And one of the alternatives is to replace part of our Portland cement and our concrete with some of the other materials. Most of the other materials that we've been using over the past 50 years are byproducts of other industries. They're waste materials from other industries, such as fly ash from coal combustion or slag cement from making steel. Now, fly ash is a material that's availability has come into question recently because of the cheap nature of alternative energy sources such as solar and wind and natural gas. And so its availability in the United States, for instance, is decreasing. Its cost is greatly increasing. One thing that we can do is we can look at what are our alternatives, and our alternatives are really natural pozzolans out there. And these materials have to be available in diverse regions around the world at low cost with a low environmental impact in order to be able to make a difference and make our concrete materials more sustainable. And I think the low cost in diverse regions is important because in order for a material to be sustainable, we have to not only make it more environmentally friendly, we also have to make it equitable and just for those around the world, not just concentrated in one location or with rich countries. It needs to be available to everyone. After all, this is about sustainable development, not sustainable status quo. We want to progress and we want to develop infrastructure to make people's lives better. We just want to do it in a way that doesn't jeopardize our future. So if we look at our options out there, we have options with other materials such as our calcined clays or kaolinite clays. These are clays that are heated up to dehydroxylate the clays in the kaolinite, and that makes them reactive for use in concrete. Our other alternatives really are not available in large quantities every year. You might say, well, agricultural residue ash, that's available in decent quantities. We can at least try to use in that. The real problem that you have with some of these other options, like the agricultural residue ashes, is the collection network. How do you develop a collection network from scratch? You either need to have it pre-existing and have the material collected for other purposes, or you need to start one from scratch. And in that case, you have to be able to get the material from the farmers that value the material as a fertilizer for next year's crops. And so you have to pay them. That raises the cost. You also have to bring it to a central location for processing. That takes energy and petrol to bring it to a central location that decreases the sustainability of the material. Also, you have impurities in the materials, like for instance, you have phosphorus in corn stover that would need to be removed in order to not damage your concrete. And that takes either a dilute acid treatment or water soaking, something like that to leach it out. And that's expensive and reduces the viability of the material. So there's a lot of issues with some of these materials. I don't want to get too much into it because that's not my main focus. But you can see that of the other alternatives, really clay is the one that has the available material that we can use worldwide to make a difference. So if we want to look at clays in our use, we can look to the past for its use. In the United States, we started using calcined materials in the 1920s and 30s. They were originally used for production of blended cements for use in, for instance, the Golden Gate Bridge. They used it in the piers and the fenders for the Golden Gate Bridge, and it was selected because it had superior performance, not because of sustainability, but because performance was better. It actually reduced the cost as well. So we can look to that past and see that it had very good performance. It was used in Davis Dam, and it was used also in the Bonneville Dam, and it was used cost effectively in those locations, and because it improved performance. In the Davis Dam, it did better with alkali silica reaction and water permeability. And so it had better performance than material with just Portland cement. So here's an example of hydration. So you can see that the use of calcined diatomaceous shale reduced the heat hydration. It reduced thermal stresses and cracking in mass concrete dams, and was valued for that. When they started looking at another material, fly ash, that came to supplant calcined clay for many decades that followed, the 50s, they actually compared it to the calcined materials performance to show that it could give you equivalent performance to the calcined shale. And that gave people confidence that, hey, we can use this material to give us as good a performance as the calcined materials, and is going to be useful for us. And this is how they justified the use of fly ash in the 1950s. It's ironic that it was justified by comparing it to calcined materials, because now when we're trying to reintroduce calcined materials back, we're comparing them and their performance to fly ash, the material that people are now familiar with. Its ASR reactivity was really good. and better actually than fly ash in many cases. So really good performance from this material, and that's why it was originally used, was because of performance, not because of sustainability. Our use of fly ash really started to increase when the Hungry Horse Dam was made in Montana. It was available almost for free because it was just being landfilled from the coal combustion. And so people started to use fly ash not because of performance, although it did perform pretty well. They started using it because it was available in cheap quantities, in massive amounts. It was available cheaply in massive amounts. Until the 1960s, the nearest source of fly ash in the western U.S. was in Kansas City in the Midwest. As more coal plants got built out west, it became much more available and cheap. And so in the 1960s and 70s, there were coal plants built in the Four Corners area and in Arizona, and that provided just massive amounts of very low-cost fly ash. And people got addicted to low-cost material. It was not viewed as necessarily a premium material, it was viewed as a low-cost material, and that's how it was used. And so the lesson from that is the economics will triumph over technical superiority almost in every case. And it was the economics that made calcined clay decrease in use, and it's going to take economics and economical reasons to make it come back. That's just the reality of markets in the United States and in many locations around the world. Now, they didn't stop making calcined clay in the United States. It was still used in Virginia, Pennsylvania in the late 90s, early 2000s, and in the Midwest and Nebraska and Iowa, mainly because they were using it to focus on alkali silica reaction durability. So again, it was used for performance. But as fly ash became even cheaper in the 1990s and 2000s, they just couldn't make it economically and compete against fly ash. And so the use of, for instance, the ash grove cement in Nebraska and Iowa, they stopped blending that material and started blending the Portland cement with fly ash. Now we're seeing that its potential is starting to come back, and people are, now that fly ash availability is starting to decrease with the shutting of coal plants in favor of natural gas and solar power in the United States. We're seeing that in the Midwest, fly ash is more expensive than cement in many regions, and now companies are starting to actually do trials to start making calcined materials again. So if we look at these calcined materials, its availability in the United States, it's available in most locations, especially where people tend to concentrate on the West Coast and East Coast of the United States. And so we have large quantities of high kaolin content clays, maybe not pure enough for making pottery or other materials, but it is available in wide regions. If you look worldwide, you have large belts of kaolinitic clay that's available to make calcined materials, typically around the equator band around the world. And coincidentally enough, it's available in locations where people tend to concentrate and live. For instance, in the United States, we have very high kaolin contents in the US Southeast, and there's a high population density there as well. So if we look at that, we have, for instance, where I live in Florida, there's a very good deposits of kaolinitic clay in the central Florida area, and especially what they call the fall line that runs through Alabama, Georgia, and South Carolina. 89% of kaolinitic clay in the United States is mined in Georgia, and a lot of it near Macon, Georgia. So we wanted to look at, for our region in Florida, how we could bring back clay use. And so there was a survey performed of sources in Florida and Georgia in our region, and we went to 9 mines and looked at over 20 different samples from the mines to calcine them and to look at their strength and how well they would perform in actual mixtures. And so based on that, found that pretty much all of them would work and would pass strength requirements for use in concrete in Florida. And so And we see this as a really good opportunity. This material is available locally and can be used. In many cases, what we found is material that's good enough to use for concrete is available as waste material at other facilities. For instance, they use kaolinite clay to make part of your catalytic converter in your car, in paints, in paper coatings, and they need high purity material for that. The material we need is found in the overburden of a lot of these mines. And so sustainable development takes a little bit of thinking outside the box. How can we use material that is otherwise being discarded? For instance, in waste impoundments from these clay processing facilities, we found material that had 66% kaolin content, more than enough and more than good enough to make a calcined material that would be economical. We also now have good tools that weren't available in the past. So if we look at the past, the 1930s and 40s and 50s, they were using characterization techniques that take a lot longer, more costly. Their calcination processes were more costly. Now we can do things more efficiently, and our science and research to identify these materials can do it in a much more cost-effective manner as well. Additionally, technology has come along that has improved the performance of materials with calcined clay. There's a material called LC3. It's a limestone calcined clay cement, and this is from a patent from Aalborg Cement that showed that if you mix some ground limestone fines with your calcined clay in a Portland cement concrete, you get a synergistic reaction between the limestone and the clay to produce carboaluminate phases. It actually gives you an increase in your strength, more than what you would expect of each material being used on their own, and increase in durability. So we can actually get better performance with lower clinker contents by using this combination. So technology has changed, and so re-examining our old ways of doing things and incorporating new technology is a way of being able to produce sustainable development and provide today's solutions. Yesterday's solutions updated to provide today's solutions to our current problems. And this material with our limestone calcined clay cement, we've examined it, and you can get very, very good durability out of this material. Sulfate attack durability, again, that's the original use of calcined clay, was for sulfate attack durability for the Golden Gate Bridge. We can find that we get excellent durability of this material and even better performance when we use a 1L cement. Some of the materials with a little bit lower calcined clay or kaolinite contents, we have to apply technologies such as sulfating to improve their performance, but our current tests show that does fix the problem. We're able to get good durability. So we have good durability out of this material. The local material that we're producing here in Florida and in Georgia, it gives you improved durability from chloride standpoint, so corrosion resistance. Again, another reason why the material is used. So we're getting a performance improvement out of this calcined clay material when it's used with limestone cements. You get this synergistic reaction for durability. We can see that with pretty much all the clays that we investigated. You get an improvement in the diffusion coefficients, meaning you get reduced chlorides and reduced corrosion from use of this materials. Even in the materials that aren't very coarsely ground, you get an eventual improvement versus the Portland cement control. But you do have to control your process, and if you control your grinding and control your quality control of your materials, then you're going to make sure that you get that performance from day one. When we look at this material, we've seen that this material is very durable and it can give you good strengths. The question then is, can you manufacture it economically? So we have a material with calcined clay, especially when used in conjunction with a limestone, finely ground limestone, that its performance is great, but can we manufacture it economically? Really your per unit cost can be 1/3 to half that Portland cement. But there's several things that you have to overcome since you're changing the system. There's capital costs that have to be adjusted for in order to be able to do this. And one is the cost of a kiln. If you already own a kiln to make Portland cement that's not being used, that reduces your cost significantly. Otherwise, it may be a $30 to $50 million investment to build a new kiln. And if you're going to adapt an existing kiln, you may have to make some modifications to control the oxygen content and control the color on it. But we know how to do this. It's just a matter of making some simple modifications to the plant. So there's the capital cost. There's also grinding. So if you're going to make a cement with calcined clay and limestone, you have to look at your grinding capacity. Are you grinding limited? Are you going to co-grind it with the cement or grind it separately? These grinding mills and ball mills can be very expensive to incorporate in. Also, calcined clay has been found, the highly reactive stuff, when you grind it fine, can reduce your workability, and that has a side effect of needing a superplasticizer to help get the workability that you need. So it's there. Yes, we can make the material at 1/3 to half the cost of the Portland cement, but you have to now use a superplasticizer, and that raises the cost and offsets some of the benefits that you have with the reduction of the material cost of calcined clay compared to Portland cement. And then the third thing is, how are you going to store the material? So just because you can manufacture it, now you have the distribution issue. So you may, at least in the transition period where you're transitioning and need multiple materials, because some clients still want the current standard Portland cement that you're producing, where you're going to store it. And that silo cost is a big expense. Because if you don't convert all of your production over to a blended cement, LC3, then you need an extra silo. So this again shows that the barriers for adoption for new technologies are mostly economics. Can you make the economics work? We know how to do it. It's just, will it work? Technological advances can only get you so far in scaling up material production and reducing the costs of production. The economics have to be there. And that in many cases means that alternatives that are less sustainable need to become more expensive in order to justify the more sustainable options. That's happening in some regions as fly ash cost is going up. In other regions of the world, for instance, in Europe, it's going up because they're taxing carbon. So you have to either raise the cost of doing something poorly or lower the cost of doing it right. And there's only so much you can lower the cost of making this new material. Another impact is, how are you going to use the material? Are you going to use it as a blended material or sell it by itself? If you sell it by itself, the market may adapt it in some cases better, but then you get performance offset. It doesn't perform quite as well as if you blend it and sell it together. So this is an example of material that we've looked at, where we've looked at it as blending it separately at the ready mix plant. If you're going to also distribute it to ready mix operations, then you have to look at how are they going to use it, your customers using it. So in that case, it's going to tend to occupy a silo at the ready mix plant, the calcined clay or the LC3 blended cement product. So in that case, you either need to install a new silo, which is going to be an additional friction in the system or inertia you have to overcome, or you got to replace a silo that's currently being used for something else. So that's another inertial issue that you have. And then you may need mixed designs for specialty cases that require you to blend your material with something else. And so that's something else to consider. It's not just the production costs that create this inertia against new materials. You have distribution networks that are very hard to change. So that's one of the things that we're facing. So the path forward, for instance, in the United States, and there are companies moving forward with calcined clay in the United States. It's being able to familiarize contractors, reduce risk and project cost. It's a chicken or the egg problem. What's going to come first? The material getting built, or the plants getting built to make the material, or contractors using it? Nobody's going to use it till the plants are built. plants aren't going to build it until people are ready to use the material. So it takes basically these demonstration projects and small scale production to then do a demonstration project to a contractor to build the demand in the contractors that they're willing to use the material before companies are going to invest money locally and that capital cost to build the plants to make the materials. So this is where we're at, and this is where industrial demonstration projects and working with contractors is really important in introducing new materials. So just in summary, just like to summarize, calcined clay that I've shown as a example of a case study of sustainable materials that one, looking to the past for solutions for our future, can often provide good ideas and solutions, especially when combined with new technologies, new ways of characterizing materials, using them, and getting more out of the materials that were there in the past. Second, it takes the economics to make it work, which oftentimes requires the old solution becoming more expensive because of those initial startup costs are very high for new materials to get them built and get them in place. And then second, or third, I should say, is demonstration projects and working with contractors is essential to reduce their risk and build the demand so that you can solve this chicken or the egg problem. So it takes resources to get these demonstration projects done. Just to acknowledge Florida Department of Transportation and Federal Highway Administration for funding this work. Thank you for your time.
Okay, so I think we can move to the last presentation before the concluding remarks. Next presentation will be from Professor Daman Panesar. She's a professor at the Department of Civil and Mineral Engineering, University of Toronto, Canada. And her research is focused on the sustainability and durability of cement-based materials. This will be another pre-recorded talk. However, Professor Panesar will be here, available to answer a question. So, good morning, Daman.
Hello, good to be with you, and please use the recording and I'll be here afterwards. Thank you.
Okay, so let me share this presentation again.
Hello, I'm Daman Panesar. I'm from the University of Toronto in Canada. And I'm going to be talking about the availability and sustainability of industrial byproducts used in cement-based construction materials. But before I would like to begin, I'd like to thank the organizers for this workshop, Professor Valentini and Professor Mawiti, for inviting me to participate in this very nice workshop. All right, so my research is focused on the durability and sustainability of concrete from new materials, existing structures, and repaired structures, and the material characterization ranges from the nanoscale to the macro scale. From an education perspective, a teaching perspective, as well as research, I incorporate the life cycle of infrastructure in my studies, ranging from the design phase, construction, use phase, and end of life. So in this talk, I'm going to be discussing the pedagogical pillars for sustainable infrastructure. And so I like to say that building and construction sits basically on a three-legged stool. There is a need for, of course, fundamental engineering design that accounts not only for innovation, but also aesthetics, flexibility of a design. The second pillar is management of existing infrastructure and structures, in particular dealing with the aging management and degradation that we see in concrete materials. And the third pillar is to, I can be bold enough to say, to solve the climate crisis, or even towards solving the climate crisis. So, of course, the status of our infrastructure is reported and publicly available. There's a wide range of infrastructure report cards. Only some of them I have on the screen here from different countries, and they're all relatively recent. And these reports basically do a critical assessment of the nation's infrastructure and rates it in accordance with an evaluation rubric. So there's different rubrics that are used for different countries, but there's also different infrastructure categories that the different countries consider. And some of them I have listed here on the screen. I'm not going to get into too much detail, but I've just selected some of the civil infrastructure categories: roads, bridges, rail, and water. And it's sort of an anonymous report. And you can see that the results are not stellar. The writing is on the wall that we all have work to do to manage our existing assets and their condition and maintenance. At the same time, as we're under this pressure to design and manage effectively so that we continue to be able to use safe and reliable infrastructure, we're also, and by we, I mean the construction industry, the cement and concrete industry, are under pressure to be more sustainable in our practices and our designs. And again, the writing is on the wall. There is a number of very recent strategic roadmaps to get us that emphasize or develop a framework for low carbon materials and technologies. The Canadian one is under development, so that is maybe the next time we speak, I'll have more information on that one. But basically, here I've just summarized some of the data. So irrespective of the country, there is typically a conservative target and an optimistic target, or a low target for CO2 emission reductions and a high target. So in general, the low target, or the conservative approach, it ranges between 18 and 37% CO2 emission reductions by the target year, which is the third column on the slide here. And typically that target year is by 2050, so 30 years from now. And these reductions are based on some historical number. So that's what the reference year is referring to here. And typically, with the exception of one roadmap here, that reference year is within the past 10 years. And in almost all cases, the target year is 2050. Well, it ranges between 2040 and 2060, but most of them are 2050. One more observation I want to make on this slide is that the high target for reductions of CO2 emissions, they're highlighted in green here. And what that indicates, and you can see some of them are 100% or more than 100%. So that means carbon neutrality or carbon negative. But the green indicates that these types of strategies include carbon capture utilization or carbon capture utilization and storage. So there is a real need for, in the next 20 to 40 years, that technology really develops for us to have any chance to achieve carbon neutral in cement and concrete construction industry. So this slide shows a lot of data from various countries. Again, it's and what I'm emphasizing here, that small plot here is from 1980 to 2017. The vertical axis is projections for cement demand. But the larger part of the plot there is the projections, the next 40-year projections. And what we can see is that globally, the overall cumulative cement demand worldwide does continue to increase. And we know that cement carries a relatively substantial environmental burden. And more refined note is that although globally cement demand is increasing, some of the wedges for some of the regions, based on the color scheme, are constant over the next 40 years or actually are reducing. So it is region specific. And so therefore, because the global cement demand is increasing, projected to increase in the next 40 years, there is a need to come up with some strategies to perhaps reduce the clinker to cement ratios. And again, all of the roadmaps address this and certainly do show that by their target year, which, whether it's 2040 to 2060, the clinker to cement ratio is reduced compared to the reference ratio. And then that reference ratio is in accordance with their reference year. And again, that varies from roadmap to roadmap. And so how will that cement to clinker ratio be reduced? The use of supplementary cementing materials is a typical approach. There's probably about a dozen other options that are mentioned in the roadmaps. I'm just going to talk about some of the more traditional common approaches for cement replacement. And these are predominantly industrial byproducts. Fly ash comes from coal combustion. Slag is a byproduct from steel industry. Silica fume is a byproduct from elemental silicon production, etc. And so, of course, the use of SEMs has some great benefits, and some of that information I have here on the slide with respect to rapid chloride permeability and alkali silica reaction. But although it does have benefits, we know that in some regions the availability is uncertain or is reducing. But if we look at coal consumption data from 1995 to 2020, we see that globally coal consumption is increasing, but regionally there could be some decreases. We also see that related to steel production. Globally, the value for steel production is increasing, but locally the production could be constant or even becoming having reduced over the past approximately 20 years. And so that's exactly the problem one of the challenges we faced in this collaborative project between IIT Roorkee and the University of Toronto. So the main challenge was related to the use of fly ash being limited by local availability and high degrees of variability. So we wanted to evaluate the interplay between material properties, service life, and economic and environmental viability. Of course, as I mentioned, SEMs, including fly ash, have many benefits, but the challenges are what we want to address here, including impacts associated with transportation of this material. So the scenario in Canada versus India is very different. Canada is in the process of closing down coal-firing plants, so we do not have very much fly ash available for us to use as supplementary cementing material. And in contrast, in India, there are projections for increasing construction of thermal power stations and therefore increasing in fly ash generation. Part of this project involved collecting fly ash from various communities in India and some reference fly ash in Canada. So in Canada, our fly ash was collected from the two plants indicated on the screen from Western Canada. And this slide shows the communities, the cities that we collected the Indian fly ash in northern India from Banga, Roorkee, and in central India in Nagpur. So the basic framework for this research was to look at the engineering material properties, as well as an economic analysis and environmental impact. So looking at a three-pronged approach to see if the benefits of the environmental material properties, how that would trade off related to the economic and environmental burdens associated with transportation of the materials. And so in other words, and very simplistically, we're sort of using a three-pronged approach, the triple E approach, which is environment, economics, and engineering. And those we would say are the three pillars of which we can build on. And so, of course, we considered codes from Canada, the US, well, ASTM and Indian standards to look at chemical and physical requirements. The chemical analysis, the oxide analysis by XRF for all of the 9 types of fly ash that we collected was met all of the chemical requirements from the 3 standards. The physical analysis was less straightforward. In some cases, some of the specimens failed the different code limits, so we needed to do some modification to the physical properties of the fly ash. So we did various grinding scenarios, and this figure shows the frequency distribution of 4 of those different cases, and we were eventually able to achieve the grinding profile that would give us acceptable physical, or it would meet the physical requirements of the tests in accordance with the Indian standard, American standard, and the Canadian standard. Beyond the actual material characterization itself, we, of course, looked at the concrete properties and performance, and what we found was that the performance was very good at both 28 days and 90 days, where all of the mixtures with the different types of fly ash from the different communities. At 28 days, we had compressive strengths greater than 25 megapascals, and at 90 days, strengths greater than 40 MPa. Similarly, our rapid chloride permeability data was quite good. We had moderate RCPT at 28 days for the target communities, and all within the range, low or very low at 90 days. So that was considered to be quite good. So once we had established our acceptable concrete material properties, then we need to look at economic viability and in the economic and the environmental aspects. The indicator we're using here is the break-off even distance, which is the maximum distance that fly ash can be transported without increasing the cost or climate impacts in comparison to the 100% general use scenario. So this just shows some of the mixed designs we used, mixed designs containing up to 50% fly ash. The life cycle cost analysis was done a fairly straightforward present value of total life cycle cost approach. This slide just shows the discount rates, the inflation rates, et cetera, that were used for the analysis. Again, this slide contains a lot of information. I'm not going to get into too much detail, but this was basically the repair and reconstruction scheme that we used. Again, it was a 100-year study period. So within that period, there would be maintenance repairs to be done on the structures, depending on the modeling that was done to achieve the time to first repair. So that, and life cycle assessment was done in accordance with the ISO 14040 standard. Our system boundary, again, included production, construction, use phase, and end of life. Again, it's a lot of details here, but again, this is just an overview of the scheme that we used. Some more model details. The functional unit that we used in this study was the volume of concrete over the 100-year study period. Time to first repair was estimated during using Life 365. And basically, when we compared our life cycle costs to our LCCA, as we, in a way, expected, increasing the percentage of fly ash lowered the global warming potential and the cost. So one figure shows global warming potential against the fly ash transport distance. The other figure shows life cycle cost against transportation distance. Rail had less burdens compared to truck. Again, this is what we had expected. And increasing transportation distance, there appeared to be a more notable effect on costs in comparison to global warming potential. But of course, we didn't only consider global warming potential. We looked at other environmental impacts, such as those on the screen as well. And one of the key outcomes from this study is that there is a nonlinear correlation between the total volume of fly ash to be transported over a 100-year study period and the percentage of the fly ash used as cement replacement. And some of those results are shown on the screen here. So that really emphasizes the need to look at this as really three moving parts in this analysis, not just the concrete properties and the durability performance, but also the economics and the trend and the environment, because certainly transportation of this material over a certain distance will influence the cost and the environmental, and of course the fly ash controls the properties and performance. So I think I'm just meeting my time limit here, so I will make some final brief remark that basically there is an urgency for responsible resource allocation, and as educators, researchers, designers, we need to incorporate life cycle design and life cycle thinking into everything we do, and a three-pronged framework of engineering, economics, and the environment is a holistic approach. I'd like to thank my sponsors for this work, and I'm also grateful for you for your kind attention. Thank you very much.
Okay, thank you, Daman. Let me see if there's any question from the chat. There are any question from the panelists about this talk? Maybe I'll ask a short question. So given that, well, somehow we're all forced to hope that in the near future we will run out of fly ashes because we will need to get rid of coal combustion. Do you think that incinerator ashes can play a role in as an SCM?
Yeah, thank you, Luca. That's a good question. I think everything has potential. We are also looking at bottom ash as a potential, but we have to be thoughtful as to how it's processed and how we can work with that material to increase the ability or its reactivity effectiveness. Thank you.
Okay, thank you. Is there any other question? Okay, so thank you again, Damon. So before I let Joseph coordinate our final discussion, well, let me just give last few words. First of all, let me thank once again all our speakers. I think it was an excellent combination of topics, very multidisciplinary. Thanks to all our attendees, participants as well. And let me thank Joseph above all, because the initial idea of having this, of organizing this workshop, it was his initial idea, and he very easily managed to convince me, although it's not always easy to convince me, but he did it very easily. So thank you very much, Joseph. And I think what emerged from today is a willingness of creating some kind of platform, of collaborating, of networking. So I really hope that this workshop can represent a starting point, and above all that soon we can meet offline. Okay, so Joseph, I will leave it up to you for conclusions.
Thank you so much, Luca, and for the kind ones and the compliments. Indeed, it has been a very good day for us. And also, I want also to thank you above all, as you said, also because of your willingness to partner with the Meru University of Science and Technology. And actually, we were thinking about an emerging university and a historical university, and to see how these two institutions could work together, one with a difference of more than 700 years or 750 years difference. It's quite a huge difference in terms of age. I also want to join you to thank all the participants and the panelists for your patience, and also for your presentations that have been quite insightful. We really learned a lot, and we hope to keep this network together. I will also wish to thank the Erasmus organization under the umbrella of European Commission, and most specifically, I want to thank Duta for finding time to also join us, and also Federico for allowing us to use his images that you've seen on the web page, courtesy of Federico Monica, who allowed us to use his image. I also wish to take this opportunity to welcome the panelists, just in case you've got some final remarks that you wish to share with us. Feel free to do so, at least 1 minute before we come to the close of this event. We hope that we can do this event perhaps next year. We have got an Erasmus program that is running for the next 3 years up to 2023, and we hope that in the lifetime of this project, we'll be able to have annual events, and we'll be getting back to you again regarding this once our plans are quite clear, and hopefully such a time next year. But before then, I would wish to welcome Gada, just in case you have some final comments, 1 minute, as we also get to the other panelists. Gada, if you can hear me, please, you can make some comments.
Thank you very much for inviting me today, and I really benefited a lot from this wonderful workshop. I have already received so many friend requests from people on LinkedIn, so I'm very happy that we are now starting to network on this basis. So welcome to everyone who would like to connect with me after this very nice day today. Thank you very much for hosting us. It was a wonderful time together. I really hope to continue on this work. And thank you, Joseph, and thank you, Luca.
Can I ask you a quick question, Gada? Gada, and extend it to other panelists as well that may want to elaborate on this. So do you think that the recent launch of the African continental free trade area can have a positive impact for these topics, for intra-African collaboration? Of course, we hope that this may shortly lead to free travel from one African country to another.
Yes, sure. I really hope so, and especially the connection with the Francophone.
Okay, I think we kind of lost a little bit of the last sentences, but well, in case perhaps you can also write on the chat.
That's okay. So thank you, Gada. Just you can write on the chat just in case you join us once more. I welcome Mark Bediako. Mark, if you can hear me.
So it is a very nice program, and the key thing is that as we are developing as African countries, such kind of programs bring us together and actually facilitate our development. So I will not say that much, but I really enjoyed the program. Just as Professor Gada was saying, I've also received some few requests from LinkedIn. We can continue to link up and then see how best we can develop our continent and then learn from best practice from the developed and strong countries. So that is what I would say. I mean, we've actually learned a lot. Yeah, so thank you to Dr. Joseph and Dr. Luca for such a wonderful organization. Thank you very much.
Thank you, Mark, and we hope to meet once again. Rain, Isaacson, if you are there, please, we would like to hear your closing remarks.
I think also Gada was raising her hand.
Oh,
I don't know if Ryan is here, otherwise.
Yeah, as we wait for Rain, Gada, please, you can have a moment to complete.
Okay.
Yeah.
Thank you so much. I lost connection, so I'm sorry. I don't know whether you got my message or not. I was talking about the mobility, that it's actually essential for good collaboration to have good training system, good airplane system. So the train that is connecting North and South is wonderful, but I would really love to see also that the Francophone and the Anglophone parts of Africa are interconnected, so that the East and the West are also connected. So with this, I would like to finish my talk, and thank you very, very much for once again for hosting us.
Thank you so much, and have a nice evening. We also wish to hear from Alistair. Alistair, if you have...
Okay. Good afternoon, Marisha. If your online signal is okay, you'll be presenting. Marisha will be presenting our conclusions.
Thank you so much, Alistair. Yes, I would like to take this opportunity to thank Luca and Joseph for putting this together. We've really had a fantastic time since morning up to this time. It's evening in Uganda, and it's been a wonderful platform where we've got to share more about what's happening with the different experiments in the different parts of the country, parts of the world. And what's amazing is how academic research fits in with the industry approaches. And it's been a wonderful session. I must say, on the side of Hailey Berry Youth Trust, we are very, very interested in hearing from others how they've managed to scale up their work, especially in bringing forward innovative materials into the commercial market space. And as well, I believe there are a number of people here who have shared about different supplementary cementitious materials, and we are looking at anyone or everyone who has experience using rice husk ash or other agro ashes in interlocking or in any compressed earth blocks, to please get in touch with us so that we can also learn from them and share what we already know. Otherwise, it's been such a wonderful session, and there's so much I've picked up personally. I've learned more about Erasmus, learned more about RILEM, and so much that has been shared. I've been taking notes this morning. So thank you very much, and I hope that this will be continued sharing, and there will be another way of networking, because there's so much information we learn from here, but we need to push it forward. So thank you very much.
Thank you very much, Mauricia and Alistair, for your contribution to this workshop. I'll now move to Fernando. I know we just had you a while ago, but you can still give your few concluding remarks. Oh, okay. It seems Fernando might not be having some comments to make. I have seen Federico Monca.
Yes, thank you. Thank you very much. I really enjoyed the approach that was really multidisciplinary and that alternated really technical issues to more broader questions. And it has been a pleasure, and it has been a pleasure in particular to see how many researchers and how many researchers are at this day in Africa elaborating on these issues. Because a big part of the world is still convinced that Africa is going to follow the others. And it's important not just that Africa develop its own way, but I think that Africa should also become an example and find new ways that the other part of the world is going to follow, because the future and a certain state of mind, creativity, and capability of doing the best by all the resources are especially developed in Africa, and I trust that this may become the future. Thank you very much.
Thank you, Federico, for your comments. I also wish to take this opportunity to allow a caller, just in case, Kolawale. Okay. Maybe Kolawale could have.
I think I don't see him anymore
okay.
in the list
okay.
of.
No problem. Then we can move to Mike Otieno.
Thank you, everyone. I think everyone is very tired now. We are in different time zones. I think it's been a long day, but nevertheless, it was quite fruitful. And first, I would like to thank the participants. I think those are the most important people for the day. Without them, this day would really have no meaning. Then I would like to thank, of course, the panelists who gave their presentations. And then last but not least, the organizers. That's yourself, Joseph, and Luca Valentini. So thanks a lot. And I hope we keep on, we keep in touch. And I think let's keep the fire burning. Let me leave it at that. Thanks.
Thank you very much, Mike. We are glad that we had you presenting this in this workshop. I welcome Daman to make comments.
Yeah, thank you. I just spoke quite a bit already, but yeah, say that if I ask myself what I'm left with at the end of the day, after hearing all of these very high quality talks on different subjects and complementary subjects, I would say that I'm optimistic about global sustainability. The leadership, of course, from my colleagues, fellow researchers and academics, but more importantly, the students and the youth that presented, that has really impressed me. Because essentially in almost every presentation, what I saw was on the ground action, on the ground experiments, on the ground communication, and integration into community. And that is really essential to see the successes and failures. And that is essential if we're going to move forward in any way. And when I say on the ground, of course, that does not exclude the excellent satellite research that was happening. So just to be clear on that, that was very impressive. So let us continue the dialogue, and let us hope that we'll meet in the future and establish new collaborations. Thank you very much, the organizers, and congratulations.
Thank you.
Thank you very much, Daman, for your comments and also for your participation in this workshop. I'm looking at whether Luca from the list. I'm not sure whether we have got the other panelists in online.
Doesn't seem so, but there's a participant who raised his hand and would like to give a statement. Victor Mutai. Let me allow him. Okay, Victor, please, if you activate your microphone. Okay.
Yes. Okay, I hope you can hear me.
Yes, you do.
Okay, I'm Victor Mutai from Meru University. Let me take this opportunity to thank you so much, the organizers, Dr. Joseph and Luca. We have followed up right from the beginning, and I can say we've learned from the vast research that has been done by many people or the presenters that were there. We've enjoyed, and we look forward to another future of more teachings, more collaborations. Thank you so much.
Thank you very much, Luca, for the feedback. And we hope that we'll be able to do this over and over again, and we'll get to communicate with you once the arrangements are ready. At this point, I would welcome Jane Duta from Erasmus. Duta, if you are with us, you can make a few comments.
I think she also left, so I think
okay.
yeah, I think all the panelists who are still here told.
I've given, okay.
So, yeah.
So thank you very much. We hope that we will be sending a quick workshop feedback survey. Take your time, and we hope to get that feedback so that we're able to make this better in our next event that we organize. And of course, we hope that it will be, we'll get more opportunities to network and to learn from the best practices as we work in the research and construction industry to better the humanity. Thank you very much, and over to you, Luca, for winding up of the day.
Yeah, well, just keep an eye at the website. As we said, we will upload presentations and videos in a couple of weeks. And thanks again, everyone. It's been a long day, but a very pleasant one. Okay.
Thank you.
Bye, everyone.
Bye.
Thank you. Bye-bye.
Bye.
Bye-bye.
Thank you.
Okay, bye-bye.
Thank you. Bye.